Well, here's another interesting topic.
Oh yeah?
Oh yeah. Yes.
Yeah, I think it is, and it's about curvature, and it's something maybe we've never really considered before. Curvature is a measure generally of how much a vector valued function is bending at a point. You could guess that lines have a curvature 0 because they're not bending at all, straight lines I'm talking about, and you'd be correct. A circle's curvature depends on its radius. Smaller circles, like the inside one here, have more of a bend than larger. In the figure below, the outer circle would be easier to bend out of the same wire than the inner, since it's bent less. In other words, we had a big piece of wire, but it was pretty heavy wire. It would be harder to bend this one than it would be to bend this one, because the curvature of this one, the outside one, is less than the curvature of the inside circle. Hence, the curvature for the outer circle is less than the curvature of the inner. So there's curvature. I hope you understand that.
Yes, indeed.
So, what is curvature? Here's our definition. Let C be a smooth curve in r squared or in r cubed, it doesn't matter, given by r of s, vector valued function, where s is the arc length parameter. Then the curvature, kappa at s, is given by kappa equals the length of this vector, and it would be the change in the unit tangent vector with respect to the change in x. And that means how fast is the unit tangent vector changing with respect to arc length. Now think about what that's saying. With a straight line, the unit tangent vector is always pointing the same way. So therefore, for a straight line, the curvature is 0. But if we have a real curvy function, then as we move along that function, the unit tangent vector changes dramatically. So I hope you can understand why this is a definition for the curvature. It's a change in the unit tangent vector with respect to arc length. So, okay, here it is. The magnitude of the rate of change of the unit tangent vector t with respect to arc length at a point P on a smooth curve C is the curvature at P. There, highlight that word, curvature at P. And so here's an interesting one. Show that a circle of radius r has curvature kappa equals 1 over r. When I write WOLOG, that stands for without loss of generality. Assume the circle is centered at the origin. It wouldn't have to be, but it's just going to make my computations a little nicer. To rewrite with arc length as parameter, if x, y is a point on the circle, we consider the arc from the point r0 to the point x, y, and let theta be the central angle of the circle, we can represent the circle as r of theta equals r cosine theta plus r I plus r sine theta j. Since the arc of s is r times theta, then theta equals s over r, and we can now write the circle with arc length as parameter. R of s equals r times cosine of what used to be theta, which is replaced now with s over r, times I plus r times the sine of what used to be theta, which is now s over r times j. And of course our r primes, this actually is kind of nice and simple. R prime of s is the derivative of this with respect to s, and if that makes 1 over r a constant multiplier, so when we take the derivative of cosine of s over r, we get negative sine of s over r times the derivative of the inside function, which would be 1 over r, and that 1 over r and this r cancel out, so we get negative sine of s over r times I. Similarly, we get cosine of s over r times j. And note, by the way, it'd be a real quick and easy study to see that the length of r prime of s is 1 because it's sine squared plus cosine squared. So we can say that the unit tangent vector with arc length as parameter is the derivative of that vector with arc length as parameter divided by the length of that derivative. Of course, the length of that derivative is 1. So it's just going to be r prime of s. And then t prime of t, we need negative 1 over r times cosine of s over r. Do you see where that came from? That's the derivative of this function. Remember, again, we have to multiply by the derivative of the inside function, which is 1 over r. So that's where this came from. That times I. Similarly, this times j. And so, our curvature is the length of that vector, which is, in this case, square root of 1 over, actually, this is negative, but when you square it, you're going to get a positive anyway, so it's negative 1 over r times cosine of s over r squared plus 1 over r times sine of s over r squared. And of course, what happens then, you're going to get a 1 over r squared that will factor out, see? And then you'll get a cosine squared plus sine squared of s over r, which is, of course, 1. And the square root of 1 over r squared is just 1 over r. So our curvature is 1 divided by the radius. I believe that's what I wanted to do. Show the circle of radius r has curvature k equal to 1 divided by r. So in other words, a circle with radius 2 has curvature a half. The circle of radius 10 has curvature a tenth. So see, a circle of radius 10 would be a bigger circle, so hence it has a smaller curvature.